We're talking about size at this panel. When it comes to anything really, energy policy, we've always been taught generally that bigger is better. The path to profitability is a simple one. You go from the lab to the pilot plant, and you gradually scale up. You go from kilowatts to megawatts to gigawatts. You shed costs, and you grow more efficient along the way. Scale is economy. But what we're going to look at here is that might not always be true. Take this number. You have each year about 250 million combustion engines in the United States convert about 1.3 terawatts of chemical energy into more than 3 trillion miles of motive power. That's all at a cost of about $35 a kilowatt. On the other end of the scale, you have around 700 oil refineries worldwide that process more than 5 terawatts of crude oil at a refinery cost of about $300 per kilowatt. That's nearly 6 times more expensive than this much smaller internal combustion engine. So it's possible that bigger is not always better when it comes to energy, and that new technologies and innovations may enable us to reduce the cost while getting smaller. And the advantages might not only be in cost. Smaller and more modular, more decentralized energy systems can be nimbler and could be a perfect fit for energy-starved developing countries that can't afford to go big. The question really is how we're going to get there, and so that's what we'll be talking about here in this afternoon's panel. We have about an hour, so I'm going to have each of the panelists introduce themselves briefly, talk a little bit about what they're bringing to the discussion, then we'll have questions here, and then we'll be taking some electronically, I believe. So if we want to start with Paul at the end, if you want to start.
I was sitting here playing around because I thought I was going to be the last to go.
Sorry.
No problem. I started life as a nuclear engineer and had a number of different pathways I followed until I retired in 2000. I was a graduate of Oregon State University, and over the course of that time, Oregon State had developed this concept for a small nuclear reactor. And small, just to give you a feel for it, conventional plants today are anywhere from 1,000 megawatts to as much as 1,500 or 1,700 megawatts. Small, in our case at the time, was 35 megawatts. Now it's about 45 megawatts. And they had the idea that they wanted to commercialize that technology. I got very excited about it, and in 2007 I agreed to lead the company. At the time, there were somewhere between 70 and 90 different ideas for small nuclear reactors that had been developed at various places around the world. Many of them used other exotic technologies. Some of them still use water. But in every case, the idea was if we're going to serve communities that have smaller grid sizes and are located in developing countries where these large nuclear plants don't fit, can we use small nuclear plants to fit that niche? And so Oregon State had developed this idea of this small plant, and the idea was it would be completely sealed. You'd load it up and you'd ship this fully loaded nuclear reactor to some place. It'd sit there for 5 years, then you'd pick it up and take it back to a factory, take it apart, refuel it, and do all of these things. Well, very quickly, I looked at that and I said, I don't know when we'll get to the point that you can do that, but it's certainly not going to be today. And if we're going to form a company that's going to commercialize this technology, we have to change the business model. We have to come up with a way to use this differently. And so we came up with the idea of taking these small units and clustering them together. So part of the point of the story is innovation happens by accident. It's not intentional. And so we came up with this idea of approaching the commercial marketplace with a different model for how you would use nuclear power, taking small units and clustering them together. And when I first started talking to investors, I would say, this takes me back to the 80s and 90s when the idea was that every new generation of computers had to be a mainframe that was bigger with more capacity and so forth and so on. And two guys in a garage figured out a different way to do it, and so I described myself and my colleague as two guys in a garage. Not necessarily a great model for selling nuclear power plants, but you get the idea. So we came up with this idea, and the biggest barrier that we had in talking to investors and in talking to the marketplace was how in the world can you be economic? It was built into the DNA of everybody in the nuclear industry that to be economic you had to be bigger. So they went from 200 to 500 to 1,000 and now 1,500, 1,700 megawatts. You have to be big to be economic. So what we countered that with was the idea that maybe if you start with a clean piece of paper and you say, are there some economies that are unique to being small that you can build into a design and capture those economies that you can't capture with a big plant. And so we argued that we had been able with our design to capture what we called the economies of small. So what are those economies? Well, in the first place, there's some things that don't scale. If you look at the pressure vessel, the amount of metal that goes into it per megawatt. If you look at the containment vessel, the amount of metal that goes into it per megawatt. If you make it smaller, it's less metal per megawatt, and it's also stronger. So there's some things that don't scale. But apart from that, when you look at making the plant smaller, suddenly we can get a very simple plant. And the simple plant eliminates all kinds of equipment that you would have to otherwise buy. And plus, it brings you an increase in safety. Simplicity had that sort of byproduct. So we gained in simplicity. But as important, we added a new feature. We added scalability, and we added an ability to build a plant more quickly by factory manufacturing these units and delivering them to the site. We could build more quickly. We could reduce the financial risk associated with building a big plant. And we could also capture what in the nuclear Navy they call the 831 rule. The 831 rule says that if you take a manufacturing process from the ship to the shipyard, you get a 3-to-1 improvement in productivity. If you take it from the shipyard to the factory, you get an 8-to-1 improvement in productivity. So by taking the entire nuclear plant that we were going to manufacture from the site to a factory where they could be mass produced and delivered to the site, we believed we were capturing a significant improvement in productivity, which we have yet to realize, obviously, because we haven't built any, but that was the idea. So we believe that we've come up with a way of building nuclear plants by doing it this way, by building these modular units that actually will achieve economies that you can't achieve with larger plants.
Garrett?
All right, thank you. I'm Garrett Van Ryzin. I'm at the Graduate School of Business at Columbia University, and actually I'm not an energy person, so that's a disclaimer right off the bat. But I got interested in this topic because Klaus, my colleague at the engineering school, and I ended up teaching a class together on sustainable energy with business school students and environmental engineering students. And just through the course of teaching that class, I was discussing with him about these issues of scaling. My background is more operations. Kind of come at this from the manufacturing kind of economic angle rather than the energy angle per se. And Klaus was dealing with a lot of alternative energy technologies and was kind of, we were discussing about how this issue that exactly what Paul said is, you always get the question of how, did things scale up, and is there a justification for new technology based on scaling it up? And he was asking the question of whether that really needs to be done. And what's interesting in the operations economic area, you'd think this would have been something that people had looked at previously. And they sort of have, but it's been one of these subjects that it's almost more conventional wisdom than something that's really been studied very rigorously. So Klaus and I ended up doing a paper on this topic, just really looking at what drives people to build technology at a large scale. What are the fundamental factors that drive it? And a lot of things are the things that Paul touched on. So one is in terms of cost. If you think of it, there's the capital cost, actually what it costs to build the infrastructure, to manufacture it. And then there's the operating cost, is once you've built it, how much does it cost to operate it? And those are the two big components. And if you drill down on the capital cost side, a lot of the rationale for building large unit size is to achieve some kind of economy of scale in the manufacturing. But sort of the flip side of that is that if you build things small and you standardize, you can take advantage of mass manufacturing, learning curve effects. And we did some rough kind of back of the envelope empirics on this, and roughly those two things scale the same way. So if you ask yourself, I'm going to equip the U.S. with very large-scale power plants, and try to bring the cost down by building these mammoth power plants, and you ask what's the total capital cost to do that, and you also look at the flip side of it. Well, what if I just mass produce to the point about the auto engine? What if I just mass produce small numbers of things? It turns out the capital cost for doing those two things in terms of just the overall level of output is roughly comparable in terms of how they scale with the total level of output. So there's really sort of two paradigms in terms of how to drive down capital costs, build it bigger and bigger and bigger and try to get the capital costs down that way, or standardize it and build just massive numbers of them and drive the capital costs down by mass manufacturing. And then on the operating cost side, we are looking at, basically labor and conversion efficiency. And one of the things we kind of realize is that a lot of the rationale for building large-scale technology is to reduce labor cost. You have to have, in most cases in the old days, you had to have an operator, you had to have maintenance people. If it's too small, that labor gets spread over too little output, and that raises up the cost. But the kind of thing that we were looking at is, does technology, in particular automation, sensor technology, communication technology, really change that equation? And I think a lot of things that Paul mentioned is that I think it's quite feasible now to think of small units that are highly censored, operated remotely, maintained by, like in Paul's case, like picking it up and bringing it back to the mothership factory. And maybe that's an alternative way of spreading labor over a large number of those small units rather than having a single operator per unit. So we've kind of sketched out sort of an analysis of these different factors. The other thing that Paul mentioned is that when you go to small scale, there's a whole bunch of advantages you get that really aren't obtainable at large scale. And these are basically flexibility benefits. So one is the ability to distribute units. So when you build lots of small things, you can distribute them geographically. That can often provide benefits in terms of like eliminating transport costs. So a good example of that is that there are some small chlorine plants now that are being developed. Chlorine's very toxic, dangerous to ship. There is a generation of small chlorine plants that are, site located, purpose built to supply chlorine in much smaller quantities that avoid the need to transport the material. Paul mentioned also this huge investment flexibility that's associated with small units. So you can build those in advance, you can deploy them in small increments as demand evolves. You don't have to take a big bet on building a $15 billion plant that takes many, many years to come online. And that actually has an option value, and like in finance, it's a real option value to having the flexibility to postpone the investment and spread it out to avoid the risk of over and under investment and things of that sort. And then on the same side, on the operating side, there's a lot of flexibility in terms of having small units and like one is just a simple reliability thing. It's like a diversification. By having hundreds of small units, the failure of any one of those units is not going to cause a major disruption. And you kind of have this statistical kind of reliability that's built into having lots of sort of a massively parallel approach to infrastructure. And so the analog that we kind of looked at here is this. It's a good analog is the massively parallel computing. If you think of it as like in the old days, there were purpose-built, large-scale supercomputers. Those dominated the landscape of computing for a long, long time. And then in the mid-90s, there was this what they call the supercomputer crash, where small-scale workstation CPUs, sort of mass-manufactured small-scale things, if you use those in large multiples, all of a sudden became more cost-effective than these large-scale special-purpose computers. And so I think a kind of interesting question to ask in this context is, could a sort of a tipping point of that sort come about? Could it be that, mass manufacturing, automation, those sort of forces get to the point where this very, very small scale technology deployed at a massively sort of modular level would be maybe a better strategy in a lot of, in the energy sector and a lot of other kind of industrial service sectors. So,
thanks. Jeff?
Great. Hello, I'm Jeff McDaniel. I'm the commercial director for Velocys and Oxford Catalyst. Our business is focused on developing and deploying modular gas-to-liquid systems. So first, let me give a little bit of background on that. So gas-to-liquids, if you walk around in the exhibit hall today, you'll see several folks who are talking about compressed natural gas. Okay, take natural gas, compress it, and use that as a fuel. T. Boone Pickens just talked about liquefied natural gas, how we super chill it, again, densify it. Our approach is a third pathway, and that's being able to chemically convert the natural gas into a drop-in diesel or jet fuel. So we don't have to change the infrastructure, we don't have to change our vehicles. We can use it today, and by the way, it burns cleaner and better than petroleum-based products. So that's our business focus. Now, the reason why I get selected, and thanks again for inviting me, Dane, to be here, is because our model is just what Garrett described. What we're taking is an alternative technology approach. We've developed what we call microchannel reactors that form the heart of this gas-to-liquids process. Now, some of you may have heard Sasol has announced that they're going to build a $10 billion gas-to-liquids project in Louisiana. So this is happening today. Gas to liquids is proven, but it is the stereotypical mega project. As someone once joked, you can see these plants from space. There's only 2 companies that can do them, Shell and Sasol. They're the only ones that have the balance sheet, the technology position, and the execution skills to make it happen. And everything about it is big. I mean, to give you one sense, a Sasol reactor, the diameter is as big as this room. It's about 30 feet. The height is 200 feet, so maybe 4 times as big as this room, and it stands up in the air, and that's what they call the FT or Fischer-Tropsch reactor. Our reactor, to put it in context, will have standardized cores that are made at a Tier 1 automotive supplier. They're 2 feet by 2 feet by 40 inches. We manifold a number of those cores into a standardized pressure vessel, and then we put them onto a truck shippable module that we deliver to the site. So that's our model of how we want to approach it. In terms of the module fabrication, one of our partners there, he has a great joke. He's the founder of the company. He says, I'll make any module you want as long as it's 12 feet by 14 feet by 40 feet, painted gray, and ships on a truck. Okay? And that's what we like. We want to leverage the economies of mass manufacturing instead of the economies of scale. We want to be factory built instead of site built, or what they call stick built in the industry. So what we've done today, now that's the model. Now part of that is through an enabling technology. We invented a reactor architecture. It was actually created out at Pacific Northwest National Labs. We coupled it with a highly active catalyst that came out of Oxford University. The 2 of them together have productivity levels 10 to 15-fold higher than today's technology. So it wasn't just standardization and mass manufacturing. There's a technology element that was really key there that allows us to radically reduce the size of these reactors and get them to the point where mass manufacturing methods can be made. So that's our model. Now, in terms of where we are, we've actually been on this journey for about a decade. We've invested $300 million. We have 2 field demonstrations currently underway, and we've announced our first 2 commercial projects. One of those is for a gas to liquids project in western Pennsylvania, kind of in the heart of the Marcellus Shale play, that'll be co-located at a Calumet refinery. The second is actually a biomass to liquids project that'll be located in London. There, the chief sponsor is British Airways, who've committed to a $500 million offtake agreement. So we're at that stage where we're figuring out how we're going to execute this and really make it happen. But it is an example of the sort of model that Garrett portrayed.
Okay. Thanks. Rachel?
Hi, I'm Rachel Sheinbein. I'm a partner at CMEA Capital, and I came to this issue because I was really doing some soul searching around what really can where's the Venn diagram overlap of what venture capital returns and energy, and what are companies that we can invest in, and particularly around ways of scaling that need to be deployed in these companies in order for them to make sense on venture dollars. There's some projects that you can take billions of dollars to build a factory, or hundreds of millions, and I just didn't think that suited the venture model, and was fine maybe for other financial investments. So I took that kind of perspective as I was looking at this, and I started by just looking at some of my own investments. And I was noticing, some was thoughtful, and some were, in hindsight, that they were either leveraging existing scale, they were doing design, assemble, and test, and taking advantage of people who have already built the factories. And then there were also the modular approach that could make sense. And at the same time as I was seeing these trends within my own portfolio companies, I also was looking at manufacturing. I went to a program that's now called Leaders for Global Operations at MIT, and they were also looking at what's happening with manufacturing and supply chain, and where has software, new materials, advanced robotics, new processes such 3D printing, snap in place, and where can all this come together? I saw these trends going on, and where can they come together to affect energy? So that's how I came to this, and then I was writing a couple articles really to solidify my own thoughts around what kind of companies can play and where we could invest. And as that's coming, I was also thinking, can venture even invest in hardware at all in any of the areas, and looking at some of that problem as well. And I thought that with these new models that that was something that we could continue to invest in. And then furthermore, there's even new funding models with things like Kickstarter and others that you can start to see what, in that case, consumer wants, but there might even be what industry wants, and all these things coming together will enable us to invest in companies that maybe we wouldn't have been able to look at previously.
Unless it's Klaus.
Thank you. Since Garrett already talked a little about the paper we wrote, let me sort of step back and sort of first have a pitch for interdisciplinary work. I've gotten to think about this a very long time ago, and what happened is we got together, and it needed that other side, the business school experience, to actually gel that into real work. But what started me was actually a long time ago when I decided I wanted to work on carbon management and deal with climate change, because I didn't see a good way of getting around fossil fuels, and then you need carbon capture and storage. And I sort of wanted to understand whether this actually is an interesting option to be involved in. And I tried some back-of-the-envelope estimates, because people said, stuff like cars costs about, at the time, $10 a kilogram, and sure enough, that gives you a $20,000 car. I said, well, if that's all true, then a power plant should be a lot cheaper than it is. And I suddenly realized, back then I had higher numbers, but it turns out a car engine sort of at the production cost is on the order of $10 per kilowatt. Your run-of-the-mill power plant is $1,000 or $1,500 a kilowatt. So somewhere there's an enormous discrepancy, and I started to bug people about why is that? And people say it's much less efficient. It turns out it's not entirely true. A car engine running at its sweet spot is about as good as a coal-fired power plant. But it doesn't last very long. And in retrospect, I think that's actually an advantage, because you can make many, many more decisions. And I actually think that's where learning comes from. If I build you a brand new power plant and you build it and we walk out of there and I say, I have a great idea how to make this obsolete, you kill me. But if you own that plant. If on the other hand, we make modules, and I say, next week we can start making some which are 30% more efficient or 30% cheaper. You think this is a really good idea. So innovation works faster on shorter time cycles, and I actually think that's why the car engine got so much cheaper in mass production, because the first rule of thumb would say they should be about the same. And how big this, so I would argue we are 2 generations away from Edison's first plant, and we are probably 20 generations away from Henry Ford's first car, and we are probably 100 generations away from the first computer. And these short life cycles, this aggressive way of moving forward, make things happen. But I do believe that you couldn't, certainly in the past, build power plants out of modules, and I'm not telling you car engines would make good power plants, of 10,000 modules equal a conventional gigawatt power plant, which would, of course, each unit is about a car engine then. Because you really would need the operators, and that would make it impossible, and maintenance, operating costs would be very much too high. But I think and that made me relatively feel good about it, because I don't want to stand there and tell the rest of the world you have been really stupid for the last 100 years and did it all backwards, because if you think that, then clearly you're on the wrong track. But if you say what really drove you up is personnel costs, and now with computers that operator can gradually be displaced, and the number of units can be separated from the number of operators. And if that link is broken, then I can start rethinking it. Take a very simple example, take mining trucks. They are not so big because they are cheaper. As a matter of fact, several hundred one-ton trucks wouldn't cost you much more than one big one. But you couldn't afford the operators. because the 3 shifts of operators running that one big truck over the lifetime of the truck cost approximately the same if you overhead them properly with having to feed people at a mining site and keep all the infrastructure in place. So at the end of the day, if you can automate that truck, like Google cars have done now, you can ask the question, was it really a good idea to go to 400 or 600 tons, or should you come back down and become more granular? And suddenly you see this question open everywhere. And as a physicist, I looked at it. For the life of me, I don't see physics arguments which say you really want to be big. Usually structures get very much more expensive if you make them bigger, as you heard in the nuclear example. But there are other things. If you look at the Haber-Bosch process, it's an exothermic process which has to shed heat, and on top of it, it needs a catalyst, so it wants surfaces. So what in there makes it all that exciting to be big? It is, again, the same story. So you want to rethink it, but I think this will be very radical because we spent 100 years of making things scale up. Now we have to make sure that as we select processes, they can be mass manufactured, they can be fully automated, and they're exceedingly robust because maintenance costs you money. So it's a new way of thinking about it, but how far you could drive costs down is very difficult to say, because think of photovoltaic panels, they got 100 times cheaper. Windmills got 40 times cheaper since the beginning. So as a result, I can get better efficiency, I can get better catalysts, and typically I gain factors 2 or 3. But mass manufacturing historically has demonstrated orders of magnitude, and that's, I think, why this is potentially a revolution. And I'll leave it at that.
Thanks very much. Klaus and Garrett, I'll start with you, although anyone can jump in on this, since you did write the paper that inspired this panel. What are the areas of energy that are ripe for taking advantage of these new economics? You mentioned chlorine factory, something that's something a little separate from energy, but what out there could you see grabbing this changing fastest?
Well, we did put in the nuclear energy example as a very interesting one, but I would argue too, and this came up obliquely several times, the coal to liquid, gas to liquid. Because you can get around this very long investment time, the very huge commitment. If I tell you you are obligated for 50 years, and you have to have a guarantee of at minimum $80 a barrel equivalent in the competition, that's a hard thing to do. If I tell you it's small increments and you are committed for 2 years, the risk analysis looks entirely different. And I think this way you could get in. So it's not necessarily that it gets greener, but it does open technology options. So this is an example. I could see this going into mining and extraction, but not so much in energy, but in other places. And so there are many, many options. Garrett?
I mean, Klaus is more the energy expert. There's an example in the paper in the biomass area as well, just because the biomass is distributed supply, so it makes sense to be able to kind of localize smaller plants close to the source of the feedstock for that.
I have a student looking at windmills, and it turns out there's no physics argument that they are getting big. Yes, they get taller, but they also get a lot heavier, and as a result, their mass actually scales faster than their power. So I think, again, what got us so big is that it makes it requires less effort to run. And so we asked the questions, what if I had a network of small ones? And I'll give you an observation. If I go to Target and buy a fan, it costs 1/4 of what a windmill costs, yet it has all the same parts.
Paul, has this argument worked with, I mean, from your experience, obviously, making modular nuclear reactors, has that argument worked with investors, with potential customers, this idea that you don't have to lay out $10 billion, $15 billion for a plant that will take 10, 15 years to build, but rather you can do it smaller? Or is there, I mean, since this is such a radical change from the standard nuclear paradigm, is that kind of a problem as well? Well,
I wish it would work better with investors, but although we've had a very good investor in Fluor Corporation, it's been interesting. When you talk to utility people, some of them are frankly sort of locked in the past, and others are quite creative. We spoke with one who had been looking at a major nuclear project and backed away from it because he said, we were looking at several tens of billions of dollars, and every time I tried to pin the cost numbers down, the vendor would back away. And he ultimately put it to me this way. He said, we were looking at a nuclear project that would be anywhere from $10 to $15 billion. It would take anywhere from 10 to 12 years to get it completed. Our money would be locked up for that entire period of time. And he says, you think about 12 years, that's 3 presidential administrations and maybe the life of 2 popes. He says, we're not going to do that. We're not going to take that kind of risk. And while your money is tied up, something could happen and the cost could go up. And now you're stuck because you've got all this kind of money stuck in the pot. So his interest in our approach was, we have an ability here to incrementally invest the money, not put it all on the table at the same time. And he said to us that even if your unit costs are higher, dollars per kilowatt, are slightly higher, we'd be willing to pay that incremental higher cost to buy down the risk associated with building these big plants. So I think we've gained some traction. I think when Babcock and Wilcox came out with their design in 2009, that added a measure of credibility that maybe we didn't have as a small startup company. But what you've seen in the industry is we came out in 2007, and I remember having a conversation with somebody at EPRI, the Electric Power Research Institute, about our idea, and you could tell as soon as I explained to him what we were planning to do, he was almost like, I've got a nut on the other end of the phone. How do I get off the line as quickly as I can? And there was this kind of pat you on the head mentality. That was 2007. By 2010, in the industry, if you went to an industry conference, they would have small modular reactor sessions, and they were packed to overflowing. And then they started holding special sessions just on small modular nuclear reactors. So it's become the hot topic in the industry because of all of these financial, I think, benefits.
Rachel, you mentioned for VCs, the high capital costs you might have with energy innovation for larger scale projects can be inhibitive. It can make it very difficult to really put that money out there. If you do, or if you are able to go smaller, if you're able to focus on those smaller scale systems, is that going to help energy innovation? Is that going to enable more competition, more ideas out there to at least get funding and hopefully get started?
Yeah, I think there is some innovation coming out of large companies who have the balance sheet to really bankroll these billion-dollar projects, but you're seeing a lot more innovation coming out of, I think, startups, and this whole conference is kind of indicative of also what's coming out of universities, research labs, et cetera. And really, I started spending a lot of time thinking about, okay, that's really cool, and if the technology works, great, but then can they even get it to a commercialization standpoint? And that's really, where we start to see change. And I think I definitely am seeing that. Just and even saw a couple examples as I was walking around the showcase today, that people are starting to think about more and more the manufacturing aspect as they're doing the technology innovation, and how can they use kind of these types of platforms, these examples that are we're talking about here, but also some of other ways of innovative ways of manufacturing. And there's a lot of interest in this country right now to bring back manufacturing here. And when we have natural gas cheap with oil very expensive, I think you're also going to see innovation of what we can even do in this country going forward. So I think we're kind of on this. It's kind of like how Paul, I remember how unpopular this talk about small-scale modular reactors, where I also feel like this manufacturing buzz, like every time I'm now at a conference, I'm also getting more and more conversation about what are we going to do differently in manufacturing, and there's a lot of interest of how that can change a lot of industries, but including energy innovation.
Well, let me sort of throw in on however there, because in a way, what worked in computers and software is that the first time, for example, I bought a CD-ROM, I was willing to spend $20. Now I pay 20 cents, and somehow or another, that ability to write down this curve was there. In the energy sector, you tend to be a commodity from day one, so it gets actually harder to get in, and even though the unit is small, in order to get the benefit of the cost scaling, you have to make a lot of them. Now, cars have done that. It's actually rather amazing. The total amount of cars we sell in a year have more power than all the power plants in the U.S. So you get to the big scale by lots of them, but in order to get cheap, you have to have it. And that chicken and egg is actually still a real problem which needs solving. And I'm not saying we have the answers to all of that.
Jeff or Paul could look at this one. This is a question from the audience. How should companies look to overcome red tape and public acceptance in small-scale projects? They use small wind turbines as an example, but it could really, I think, work for anything that might face criticism publicly, where the time and effort, where they can't necessarily put in the same time and effort that large-scale projects can because of that size. I mean, how do you deal with that? Is that a drawback to the fact that you might have to fight more battles on a smaller scale rather than just one large one?
Well, that's an interesting question from our standpoint. And there's two questions. There's a regulatory question and there's the public question. The response of the public to our design has been interesting. Even people who have been typically skeptical are more willing to have their skepticism, I'll say, addressed, because intuitively you can look at a design like ours with its simplicity and its size, and it doesn't feel as big and complex and therefore risky as a big plant. Whether it is or not is another question. We don't think it is, obviously. But the public has been receptive to this design. One of the questions I get asked is, what's been the reaction to Fukushima? And we of course had the problems with Switzerland and Germany and countries like that basically backing away from nuclear power. But there have been others that have actually gravitated towards smaller reactors in the wake of Fukushima. And there's a whole series of articles that came out right after the accident that talked about maybe they're the design of the future. So from the standpoint of public, we haven't had a negative reaction. It's been, if there was a balance, it would be on the positive side. On the regulatory side, it's also been, I mean, you can't say there's no red tape in the nuclear business, because every approach you take will take a long time today. But the regulators have also typically reacted in a positive way, in part because they see the safety benefits and the quantum improvements in safety and the quantum improvements in safety that are just sort of inherent in looking at the design. So from our standpoint, I think in both of those sectors we haven't run into resistance. I think we've run into a very receptive audience.
So our case may be a little different than Paul's in that we have a wide range of applications and types of uses that we can pursue. For the fundamental technology we've developed, the FT, it can be applied to natural gas conversion, biomass conversion, and coal conversion. And I'll tell you candidly, we prioritize those and we focus on the ones we think have the best chance of winning. At least in the early stages, we focus on where we can control and what we can influence, which is around the technology itself, and try to minimize those external risks wherever we can. So there are certain ones where we say, that looks really hard, not from a technology standpoint or other standpoint, but there's external barriers that I don't have the resources to fight. So in those cases where we want to pursue them, if we're going to fight them or we're going to think we're going to encounter some resistance, I want to make sure I've got a big partner who's on my side, who has the wherewithal to help me overcome them. So that's just kind of a pragmatic, strategy that we have. Since we have flexibility, we tend to look at ones that won't be as challenging as others.
There are well over 1 billion people around the world who lack really any access to electricity, and the chance of creating a U.S.-style grid, I think, with a large centralized power system for those parts of the world it's going to be challenging in the long term. So, and anyone can really grab this one, but do you see developing countries taking special advantage of that sort of small-scale system? Is that something where they, because of a lower barrier to entry, will be able to take advantage of this first, perhaps even more so than more developed nations? If anyone wants to volunteer there. Sure.
I'll answer not on the power side. Okay, so one application for ours is actually dealing with natural gas flaring. So, right now we produce oil, and many places we produce associated gas that we don't have a good home for it. So we flare it or we burn it. We burn about as much natural gas, or if we could capture all the natural gas that we flare, we could power Germany and France combined. That's how much we burn. And that's been banned in a lot of places, so there we re-inject it into the field. We re-inject 2 times that amount and that we flare back into the reserves. So the vision that's been out there, gosh, well, if you could do gas to liquids and you could do it in a small modular manner, can't we convert that natural gas into more crude oil and then ship it along with the crude oil we've already produced? So that would be an example. And you look at what are the leading flaring areas, they end up people like areas like Nigeria and West Africa and Siberia, really remote places. So it doesn't help on a power standpoint, but the ability to take a process and make it modular and scalable to a smaller scale does open an area to address a very significant environmental issue and help create more economic wealth in remote areas.
If scaling up is your approach to driving costs down, then you of course disadvantage those who don't have that large demand. So the unfortunate outcome of this, that electricity in this country is a lot cheaper than it is in poor parts of Africa, and poor people who get electricity end up paying a lot more. As a result, very many don't have any, and so I would argue this is a little bit like the leapfrogging you might have seen in cell phones, that if we move to a technology which competes successfully against the large systems but is small, then you naturally can export that into this situation. And we may be open to clustering, let's say making a big power plant of 10,000 units and have it centralized, but then if you are in Alaska, you still would have, near a small village, you would have 5 units, and in an African village, you would have 1. Right? But you suddenly open the door to affordable energy everywhere, and that I think is very powerful.
Paul, there's a question for you from the audience. It's about is there an increased risk of proliferation when it comes to using those small-scale nuclear reactors, if you are moving them around the world? I know that's something you deal with. One would just sort of assume that more plants could mean more of a risk, but what sort of safeguards are there against that?
Yeah, I'm glad you asked that question because it sort of nagged at me that in my opening remarks I left the impression that we're shipping fully loaded reactors around the world, and we're not. That was the original idea. We're not doing that. That's not part of the plan. What we do is we build the reactor vessels, take them to a site, and all of the loading and unloading of fuel occurs at the site. And to that extent, it's exactly the same kind of issue that you have with conventional nuclear power plants. All the loading and unloading and the management of fuel occurs at the site, and it's all taken care of there. All the security is there. So there is really no difference on the proliferation side of the risks associated with our plant versus conventional nuclear power.
Another question from the audience. Maybe Garrett, you could look at this. What impact do you see are there benefits to installation costs when it comes to going modular?
Installation. Yeah. I mean, the sorts of things that we've looked at, I think there's just an enormous number of benefits around standardization. So, I mean, to Paul's point, I think it's not, every plant's not a somewhat unique design that has to be certified separately and things like that. You can have a standardized design that can go through certification once and then be deployed in a lot of locations. And I think the installation is the same sort of issue, is that you have a standardized design that works in a predictable way, and so it's a matter of it's sort of a plug and play kind of proposition to kind of, it's manufactured, you ship it there, you know how to operate it because you've done it in many places before. And so I think there are a lot of economies to just that standardizing the operation of it, so certainly installation is one of them.
I had a comment. So the way we build at least chemical plants and GTL plants today, and a lot of power plants, is the phrase I used earlier, stick built. We take all of the pipes and pumps and compressors and controls, and we haul them to wherever that site is, and then we send a bunch of engineers and technicians and welders, and we build it from the ground up there. So if you can make the units smaller, you can apply a modular approach where we basically put it together in a factory. So we move. So our rule of thumb is we expect for the capital cost of 1 hour facility, about 70% of the cost to be built in a closed, low-cost environment, and then the 30% to be the installation, site preparation, installation startup, etc. So that's what we've seen, at least based on the engineering studies we've done so far for the various sites we've looked at.
There's another aspect to which is maybe not directly installation, but the modularization and standardization also allows you a plug and play. For example, in your case, you said you have biomass, you have coal, you have gas. And so if you mass produce modules, you can have an intermediate stage where you have synthesis gas and you have different modules up front, but always the same behind. And suddenly the numbers you make get larger because they are not just given from one side, but from another. And I would argue one of the big advantages, for example, Dell's business model was that you don't have to make all the bits and pieces in-house. You get standards which can come from different places and which fit. So just like you have IEEE standards for USB stick and all of these, you need to get them here then too, so that you can fit things together in a way which makes sense. But then you can use off-the-shelf pieces to make all sorts of applications, and that's another advantage you get out of this mass-produced approach.
I have another question from the audience that actually follows up somewhat on that, and they're wondering whether 3D printing is at odds with small scale and standardized parts, and whether the customization, the complexity you can get with 3D printing might actually make standardization less important.
No, I actually think there's going to be a big transformation, and kind of talk about you have to now screw things together, weld things together, versus design something on a computer and print. And I think, and tweak it with a mouse click. I think it's still, though, having, standardization, I can think about implications to spare part management. I mean, now, I was talking with, we check in closely and always talking with different strategics. And the other week I was meeting with the guys from ABB, and they were just talking about how much of their balance sheet is inventory for spare parts management, and how 3D printing can totally change that. But I don't think they're going to want to do customize every time. What it's going to enable is that they can have just a 3D printer in different locations all over the world, instead of these large distribution centers and all the people and all the infrastructure behind managing it, and that it can be sent from wherever it's needed and printed there and all automated. And I think that even it could help with doing things more custom. On the other hand, standardization could really help that type of supply chain work, because then it's easily done from anywhere, and reduces the people and the complexity of it. And so I think I would never say obviously some models that we talk about at that you do everything standard, and then the very end is where you can tweak it, and it enables that. On the other hand, think about the benefits of also standardizing in this case, I think are huge. So
I was going to say there's also another way of thinking of that whole 3D printing thing as modularization and standardization of manufacturing itself. That rather than having special purpose plants that only produce one product, you have these modular, generic kind of printing plants all over the place that can produce products. So in some ways, it's almost the manufacturing infrastructure analog of what we're talking about.
Right. It seems like it fits hand in glove with a more distributed way of building things.
Yeah.
Exactly. Yeah.
You were getting towards the end. Are there disadvantages to going small? I mean, are there areas, just again, where you've looked at this, where you found that those economies of scale still hold up, that it's still better to be bigger?
I hate to answer this question, but the big issue that we have is if we build a 540 megawatt unit, there's 12 units. There's 12 turbine generators, there's 12 condensers, there's 12 of all the support systems that go with it. And so the big challenge that we have, and the big question that people ask us is, you've got 12 of everything versus 1 of everything. How can you possibly run it cheaper? And there's some trade-offs there. So we think we can get around that. But that is the big, get away from the theoretical economies of scale that everybody's bought into. When it gets down to taking the veneer off and starting to ask pointed questions, that is the most difficult pointed question that we have to answer. We think we've got answers for it, but that's a big one.
I think I would argue the following. Historically, there was a very good reason for just about every industry to say big is better. And so you didn't have to think about it. Right? Now you have to think about it. And in some cases, big is better. Right? If you want to contain heat and that's your dominant problem, you better make this thing as large as you can possibly do, because that will contain heat. The point is, sometimes the physical laws will drive you large, sometimes they will drive you small. Having looked at a lot of things, I think it's actually more often that it drives you small. On the other hand, I would say we spent 100 years in making decisions. Take Fischer-Tropsch. Again, it's a catalytic process which is exothermic, so it's actually not that easy to understand why it wants to be that large. It buys itself a lot of problems doing that, but it does. If you look at it, for 100 years, engineers have looked at it and said, does it scale up or not? If it didn't scale up, this was not an interesting process. So we selected systematically over 100 years that one process which really wants to be big. If I say, let's just turn this around, this will not happen overnight. So this is a long process in front of us, and you can sort of view me now as a theoretician who says we have to push that way, but it won't happen overnight.
I would say, besides the physics argument that Elon Musk mentioned earlier and agree with Klaus, I also believe that there's just a lot of innovation when we take off the shackles of how we always went at the problem. And so just opening up and what has already come to be with changes, in software and how we can get work done. I think there's a lot of unknown. Besides, the physics is known, but then beyond that, there's just questions we didn't ask because I don't think we had the tools. And as we're creating more and more of these manufacturing tools, I think that's just going to open up again oh wow, we hadn't even thought of that. Oh wow, we can now do this. So I feel kind of optimistic. I guess that's why I'm in this business of investing in innovators, is that there's just some problems that are going to be solved in ways we haven't even imagined yet, and so I think that's really encouraging.
Well, I think that's a pretty good place to end it. Thank you to the panel. Thank you to the audience. Hope we have a good conference.